So this is the first video on graph theory, just basic introduction and some definitions. So intuitively, a graph is just a bunch of points that are connected by straight lines, and that's the intuition for what a graph is. But to make this formal and mathematical, and to make it something that we can, prove theorems about and put into computers and things, we have to be a little bit more rigorous in what we say a graph actually is. So the formal definition of a graph is given right here. A graph consists of an ordered pair V and E. V is a set of vertices. Those are the points. Okay, so this is the set of points. And then E is another set. That's the set of edges. And an edge, E, well, these are the lines connecting the points. That's what the edges are. And an element E, little e in big E, looks like this. It's two different vertices, okay? And if E is equal to xy, so if I have a vertex x and a vertex y, and if E is equal to xy, that means there is an edge connecting those two vertices, and this would be the edge E. All right. So a graph that is simple is a graph that doesn't have any loops. Okay, I don't have anything like this in a simple graph. And I also don't have multiple edges. That is, in a simple graph, I don't have anything like this. I'm not going to have more than one edge connecting the same two vertices. That's in a simple graph. So let's look at this example in this box right here. This is a simple graph. So the vertex set is given by A, B, C, D, E, and F. So notice there's a picture right here of the graph. I'm going to draw the same graph, but a little bit differently, because I want to show you that graphs can have more than one representation. So there's A, B, I'm going to put C here, D, E, and F. So there are my vertices. And then here's my edge set. So AC is in my edge set, so I have a line connecting A and C. AD is in my edge set, so I have a line connecting A and D. BD, so this line is in here. BF, so that line is there. CF, that one is in there. DF, this one is in there. And FE, this one is in there. So these two pictures represent the same graph. Even though they look differently, they're the same graph because they have the same set of vertices and the same set of edges. Now, I want you to notice that even though those two edges cross each other, there is no vertex there, okay? Because there's no point drawn and there's nothing labeled, so there's no vertex there and there's no vertex there. So there are no vertices at those places, even though it looks like those edges cross over each other. Just as a graph, there are no vertices because they're not part of the vertex set. Okay, moving on. We have something called a directed graph, and a directed graph is defined right here. Another word for it is digraph, and it's an extension of the definition of the graph, but now the edges are ordered. That is, they have direction. Okay? So here I have a graph FE with vertex set A, B, C, D, E, and F. And now I'm declaring beforehand that this is a digraph. I'm going to go ahead and say in advance that this is a directed graph. This is a digraph. So that means all of these edges are going to have arrows on them, indicating which direction the edge goes. So I'm going to draw this graph again to show that we can symbolize it different ways. But notice one thing right here. When I write down in a digraph AC, that means the direction of the arrow goes from A to C. It goes like this. So whichever one comes first is where the arrow originates, and whichever one comes last is where the arrow terminates. So here I have my A, B, C, D, E, and F. This is my vertex set. And now my edge set, I have AC, so I have an arrow going this, I have a vertex going that way. I have DA, so I have an arrow going this way. I have BD, so I have this edge. I have FB, so I have this edge. I have CF, so I have this edge. I have DF, so I have this edge. And I have, sorry, that's a typo. That shouldn't be G. That should be, and I'll fix that. That should be an F. So this is an F. So by the time you watch this video, this will probably be corrected in the text. All right, so I have FE. So again, these represent the same graphs because they have the same vertex set and the same edge set. And again, even though I have these crossings, those do not represent vertices. Okay? Now, a very important and fundamental concept in graph theory is the idea of the degree of a vertex. And all the degree is how many edges touch the graph. Excuse me, touch the vertex. So I have the degree of a vertex. This is how we denote it. D of V is just the number of edges that contain the vertex V. But intuitively, it's just how many touch it. Okay? So let's go ahead and draw this graph, V and E, and we'll look at a couple of these and see why those are the degrees. So I have A, B, C, D, E, F, and G. And then I have AC, whoops, let me label them, A, B, C, D, E, F, and G. So let me label them. So I have an edge A to C. Now that they're labeled, I can go ahead and draw my edges. I have an edge A to D. I have the edge B to D. I have the edge B to F. I have the edge C to F. I have the edge D to F. And I have the edge F to G. Okay, and you can see that I made a slight correction in this, some more typos. That'll be fixed. So I'm just going to talk about the just a couple of them. So let's look first of all at A. Okay, so notice that A has two edges touching it, so the degree of A is equal to 2. Another way to see that is if you have your edge set listed out like we do right here. Just see how many of the ordered pairs have A in them. Well, there's 1, there's 2, and no more of them have an A, so the degree of A is 2. Let's look at D. D has 1, 2, 3 touching it, so the degree is 3. If we count how many of these ordered pairs have D in them, there's 1, there's 2, there's 3, and so on and so forth. Okay, so you can go ahead and look at what the degrees are that way. If you have the edge set listed out for you, then you can just check which vertices show up in the ordered pairs. If you have the graph drawn out in front of you, you just look and see how many edges connect to that vertex, and that will be the degree. Now, a very important theorem is called the Handshaking Lemma, and it tells us that the sum of the degrees of the vertices of a graph is twice the number of edges. So formally speaking, this is what we're saying right here. This means sum. If you add up all the degrees, you get 2 times the edges. So let's look at a simple example. Let's let G be equal to A, B, C. And that's my vertex set. And then my edge set E is going to be AB, BC, and that's it. That's all. We'll just have AB and BC for this graph. So if we draw this out, this is A, B, C. So I have AB, and I have BC, and that's all. So let's add up the degrees. So the degree of A plus the degree of B plus the degree of C equals, well, the degree of A is 1 because there's only one vertex touching it, one edge touching it. The degree of B is 2, and the degree of C is also 1. So that gives us 4. Well, how many edges are there? There are 2 edges. So 2 times the number of edges is going to give us 2 times 2, which is also 4. And so, yeah, the handshaking lemma tells us, gives us that those 2 numbers should be the same. This is really useful when we consider the types of graphs we can have in terms of their edges and their degrees. This can say, well, some things can't be graphs just by virtue of they have the wrong number of edges and with the wrong degrees. And we'll see what I mean by that in just a minute when we look at some example problems. Okay? That's all that I wanted to say in the introduction. So let's go ahead and look at the notes quickly, and then we'll do some example problems. After I erase all of my scribble. Okay. So in the notes, again, read through these. It just reinforces the ideas. I do have some examples of non-simple graphs. This is a simple graph, this one here, because there's no loops and there's no multiple edges. Here's a non-simple graph that has multiple edges. Here's a non-simple graph that has loops. Here's that example of a directed graph. And, here's a great video to watch that gives some more examples. Here's a video you can watch about calculates degrees some more. Here's a really nice example that I want you to think through. How many edges are there in a graph with 10 vertices, each of degree 6? Well, we're trying to count the number of edges, okay? And the handshaking lemma gives us this, that the sum of, over all the vertices, if you add up the degrees, this is going to be 2 times the number of edges. Well, if there are 10 vertices, each with degree 6, if you add up all of them, add up the degrees of all of them, this is just going to be 10 times 6, which will give you 60. And that has to be equal to twice the number of edges. Divide both sides by 2. And we'll see that the number of edges has to be 30. That's what I mean when I say the handshaking lemma or handshaking theorem lets us solve some problems. There's another video that goes over the same idea. And then we have these practice problems, which we're going to do right now. All right, this first example wants us to draw some graph models and tell whether it's a simple graph, a multigraph, or directed graph to represent airline routes, okay? So here's the really neat thing. I've drawn vertices for each of the cities, Boston, Newark, Miami, Detroit, and Washington. And notice these aren't geographically accurate. Like Boston is not, in this relationship to Detroit. It's not like northwest of Detroit, but that's okay because the graph model doesn't matter. We can still draw it this way. So in part A, so I'm gonna do all of these on the same set of vertices. So let's do part A first. We're gonna draw an edge if there's a flight between the two cities in either direction. Okay, so we're saying if there's any flight at all connecting the two cities, draw an edge. So first we have that there are 3 flights from Boston to Newark. Well, we draw an edge if there's any flight, so I'll draw this edge here. Next, so here's the first piece of information. Second piece of info is there are 2 flights from Newark to Boston. So I already have an edge connecting Boston and Newark. Next, we're told there are 4 flights from Newark to Miami. So remember, I draw an edge if there's a flight connecting the two cities. So I have an edge from Newark to Miami. Next, I'm told there are 2 flights from Miami to Newark. Well, I already have an edge there. There is 1 flight from Newark to Detroit. So there's an edge here connecting those. There are 2 flights from Detroit to Newark. I already have an edge there. 7, there are 2 flights from Newark to Washington. So I have an edge here. 8, there are 3 flights from Washington to Newark, or I already have an edge connecting those 2 cities. And there is 1 flight from Washington to Miami. So I have an edge connecting those 2. So that's all I have to do. This is the solution for part A, because I just have edges representing cities that have a flight between them in either direction. Okay. Now, how does this change if we're going to do part B? Well, let me erase these edges that I have drawn in. And now we're going to consider part B. So let me go ahead and fix my D here. And now we're going to consider part B. Now I draw an edge between vertices representing cities for each flight. So for each individual flight in either direction, I'm going to have an edge. So looking here at what we have for 1 again, there are 3 flights from Boston to Newark. 1, 2, 3 flights from Boston to Newark. Looking at part 2, there are 2 flights from Newark to Boston. Well, I already have those 2 represented with the lines that I've already drawn. 3, there are 4 flights from Newark to Miami. There's 1, 2, 3, 4. Then there are 2 flights from Miami to Newark. I already have those drawn. Number 5, there's 1 flight from Newark to Detroit. So from Newark to Detroit, I have 1 flight. And then there are 2 flights from Detroit to Newark. So I need to draw another edge connecting those 2 cities because I have an extra flight that goes from Detroit to Newark. Number 7, there are 2 flights from Newark to Washington. So there's 1 and there's 2. There are 3 flights from Washington to Newark. So I need to put another edge here for that other flight. And there is 1 flight from Washington to Miami. So I'm just going to draw this like this. Okay. Sorry, in A, these were all simple graphs. These were all, in part B, I have multi-graph. So part A, it was a simple graph because there were no loops, there were no repeated edges. Part B is a multi-graph because I have repeated edges. Okay, so that's what this one looks like. And now we're going to look at part C. So let me go ahead and undo all these edges that I had drawn in. And then erase these best that I can. Okay, so now, and once again, part A, that was a simple graph. Part B, that was a multi-graph. And part C, in part C, we have an edge from a vertex where a flight starts to the vertex representing the city where it lands. Okay? Now, I'm not going to do this one. I'm going to leave this as an exercise, except for A. Okay? So C says, I have an edge from a vertex representing a city where a flight starts to the vertex representing the city where it lands. Okay? Now, in this one, I'm not going to have any multiple edges because it just says when there's a flight that starts somewhere and to where it ends. So number 1, there are 3 flights from Boston to New York. Starts in Boston, ends in New York. So that is a directed edge. Okay, so I'm going to leave this as an exercise for you to finish. But you'll just go through those 9 pieces of information, and you, instead of drawing, just edges between the cities, you'll draw you'll draw directed edges between the cities. Okay, so let's move on to the next example. All right, this example gives us 3 graphs, part A, part B, and part C, and we want to find the number of vertices, the number of edges, and the degree of each vertex. Okay, so I'm going to do, I think, A and B in this one. No, I think I'm going to do A and C. Okay, So A, how many vertices are there? 1, 2, 3, 4, 5, 6. That's easy. The number of vertices is 6. How many edges? 1, 2, 3, 4, 5, 6, 7. The number of edges equals 7. And I'm just going to write the degrees beside the vertices. So A has degree 2, B has degree 2, C has degree 1, 2, 3, D has degree 3, E has degree 2, F has degree 2, and that's all there is to it. Okay? For part B, the number of vertices is 4, the number of edges is 1, 2, 3, 4, 5. The degrees are 2, 2, 1, 2, 3, and 1, 2, 3. So that's all there is to it. As long as you know what a vertex is, what a vertex is, what an edge is, and what the degree is, I don't think you'll have any trouble at all doing this type of problem. This last example is a little bit more theoretical. It asks us, can a simple graph exist that has 15 vertices, each of degree 5? Okay, now, how do we approach a problem like this? Well, one idea is to just draw some graphs. That might be the first idea you have to approach this. Not the best idea, because there are 15 vertices, and you're trying to give each one of them degree 5. So for each vertex, you're going to try to have, 5 edges touching it for all 15 of them. That's a lot of work, and you'll probably get frustrated before you find an answer. So a better idea, whenever you have a theoretical problem like this, is to think, do we have any theory that can help us with this? Do we have any theorems or lemmas or anything that talk about number of vertices and degrees and things like that? And we do. We have the Handshake Lemma, or Handshake theorem, which says that the sum of all the vertices in the vertex set, if you add up all of their degrees, you get 2 times the number of edges there are. Now, notice that there's nothing in this example, the statement of the problem, that talks about edges, okay? But what do we know? We know that it's 2 times the number of edges. And we know that if you multiply anything by 2, you're going to get an even number. Any number times 2, the result will always be even. So that means if we add up the degrees of each vertex, that has to be an even number. Okay? So if we assume that it is possible to have a graph with 15 vertices, each of degree 5, well, if we try to apply the handshaking lemma, then adding up each one of these, adding up all the degrees, is going to give us 15 times 5, which is 75. But that's a problem, right? That is not an even number. So the handshake lemma says that if you add up the degrees of each vertex, it has to be even. And if we assume that this statement is possible, we get an odd number. That means that statement is impossible. So the answer is, there is no graph, no simple graph with 15 vertices, each of even degree. It's impossible for that to happen because of the handshake lemma. And that's how you'd solve a problem like that.